This is part one of the Digital Dynamics Studio walkthrough tutorial. Today we're going to be setting up the exam problem that we're going to be simulating, walk through why it's set up this way and what are some of the parameters and how you need to design the problem that you're going to simulate. Here in this figure, you see that we're going to be simulating fluid flow past a cylinder. This is a very common and typical example that is studied often in numerical methods and numerical simulation. As you can see in the figure here, we got a cylinder at the middle at the origin of the xy coordinates. That's location 0.0 with a radius of 1.0. And as you can see and highlighted in green, the fluid flow is coming from the left, flowing around the cylinder and leading on the right. The blue outer boundary that we can see around the perimeter, that's the limits of the computational domain. Um, of course, in this example, the fluid is everywhere. X, in both coordinates, off to the left, to the right, up and down, but we can't simulate the fluid everywhere. That would just be too expensive computationally. So we have to kind of limit the zone of where we're simulating the fluid, and that's defined by the spots, which defines the computational domain. You want it to be big enough that it encompasses the geometry and where we think the exciting, interesting fluid flow is going to happen. And as you can see in this figure, that's generally the green region since the fluid is coming from the left. So we can go around the cylinder and the wake is going to develop behind the cylinder within this green region. That's what we would expect. We'll see when we do the simulation, but that's kind of what we think will happen. So you want the domain to be large enough to encompass all that region. If it's too small, it'll, have an effect on the results and you won't be generating accurate simulation results for your example. So you want it big enough so that the location of these outer boundaries, in this case it's a rectangle, the top and bottom boundaries and the left and right boundaries, they're far enough away that they're not going to have a significant effect on the results of the simulation of what's happening with the fluid. But we can't make it too large, otherwise the computation will become too expensive. We're simulating parts of the fluid flow where nothing is really happening, so we're wasting computation. So we don't want it too big. But again, we don't want the outer boundary to be small enough that it has an effect on the results. So you can see here in this example, we have the fluid is coming from the left. That's called the inflow boundary. That's where the fluid is entering the domain. And in this example, that's located at an exponent of -10. And the right boundary, it's longer, of course, because in the screen region, that's where we expect the wake behind the cylinder to develop in the fluid. So we need enough space here to accommodate those results. That's what we want to see. We want to see how the fluid behaves as it goes around the cylinder. So the right boundary where the fluid is going to be exiting is 30 in the x direction. That's far enough away that we'll see everything that we want to see in the wake behind the cylinder, but not too far that we're just wasting calculation. As you can see here, the top and bottom boundaries of our computational domain are at plus and minus 10 units. And that's far enough away that the effect of that boundary won't have any significant influence on the fluid that's developing in the wake behind the cylinder. It could be a little bit larger, but these are good coordinates to start out with, and that's what we'll be using in our example here. In order to set up the flow problem properly, we have to define boundary conditions. You can see here we have 5 boundaries. We have the cylinder itself, the left boundary, which is assigned to number 2. The cylinder is assigned to number 1. The right boundary, as you can see, is assigned to boundary number 4. And the tops and bottom boundaries are assigned to boundary number 3, as you can see in this figure here. We need to assign boundary conditions to each of those boundaries, which basically specify what's happening with the fluid along those boundaries. We don't know what's happening with the fluid in the interior of this computational domain. That's what we're solving for. That's what we want to see as part of the results. But we do know or suspect what's happening with the fluid on these boundaries. So we have to specify boundary conditions that tell the solver how to treat the fluid along those boundaries. So you can see in boundary number 2, which is the inflow boundary, that's where the fluid is entering the domain. And in those boundaries, we basically specify the speed of the fluid along that boundary. And that's going to be the main driving force, driving the fluid through the domain at the specified velocity that we want it to be. So we're going to call that an inflow boundary, and we're going to specify a fluid velocity of 1.0 in the x direction and 0 in the y direction along that boundary. And that's going to be the main speed of the fluid going through this computational domain for this example. The tops and bottom boundaries are assigned to boundary number 3, and those get the x-slip boundary condition. We don't know what the velocity is in the x direction along those boundaries, but we do not want the fluid to penetrate that boundary. We don't want it to go through that boundary. So the x-slip condition allows the fluid to slip along that boundary in the x direction, but sets a 0 velocity for the fluid in the y direction, which ultimately says that fluid can't leave the domain through that boundary. You can only slide along it in the x direction. The boundary here on the right, which is boundary number 4, we're going to assign the outflow boundary condition along that boundary. And that's basically just allows the fluid to exit the domain cleanly. The solver is going to do a couple special things along that boundary to allow the fluid to exit cleanly and efficiently. But that's the outflow boundary. We're allowing the fluid to exit the computational domain along that boundary. The final boundary, of course, is the cylinder itself. And that is boundary 1, as you can see here in this figure. The fluid on these, it's a solid boundary, and fluid along these solid boundaries can't slide along it. The velocity of the fluid along these boundaries must match the speed of the object, and the cylinder is going to be stationary. The flow is going to be moving around it, but the cylinder itself is going to be stationary with a velocity of 0.0. So we want to assign a velocity of the fluid along that boundary to have that same velocity of 0.0, and that's called the no-slip boundary condition. So we're going to assign the no-slip boundary condition to boundary number 1, and that's the general kind of boundary condition that we would apply for objects that are kind of stationary within the fluid. That's the no-slip boundary condition. Again, to highlight with these boundary conditions, the flow is coming in from the left here along boundary number 2. It's going to exit on the right here along boundary number 4. It's going to flow around the cylinder, and there's going to be a wake that develops in this green region behind the cylinder. So this is a typical problem setup. It's fairly simple, fairly straightforward, but it's a very common setup in many numerical simulation experiments. So that's it for part 1. In part 2, we're going to create this model within the modeling tools of the Digital Dynamics Studio and continue with the steps to perform the simulation in part 2. So we'll see you then. Thank you.